Hello, everyone. Can you hear me? Okay. Good afternoon, everyone. Welcome to Tsinghua University Global Open Course Future Automobiles. And today, I will present the safety of the intended functionality for intelligent connected vehicle. And first, let me introduce myself for briefly. I'm Hong Wang from Tsinghua University, and it is from SVM, the School of Vehicle and Mobility. My research area is around the decision making, task planning for autonomous vehicle, and now especially for the safety of the intended functionality, SOTIF, for autonomous vehicle. So today I will take you to look at what is SOTIF for intelligent connected vehicle. As far as we know, safety. I don't know whether you can know this SOTIF concept or not, but some people think SOTIF is the engineering problem, but I disagree with that. I think SOTIF is both engineering and academic research problem. So let's look into what is SOTIF and how to solve it. So today I will bring three parts of this course. The first one is what is SOTIF for ICV. So in my previous or later slides, I will use the abbreviations. SOTIF means safety of the intended functionality. ICV means intelligent connected vehicle. So the second part is how to solve this problem. And third one is what we are doing inside of our research area or inside of Tsinghua University. So as we know that developing autonomous vehicle is to reduce or eliminate the traffic accident caused by 94% human errors. So as US DOT announced the development of autopilot, while DOT HTSA also released the vision of self-driving car safety. So we have the expectations that develop the autonomous vehicle can reduce or eliminate the human error around 94%. But the reality is that with the development of the ICV, intelligent connected vehicles, we have the perception, the measurement and verification technology issues, which brings the new accident to humans. In 2016, the world's first automatic driving accident. And in May 2016, one automatic vehicle hit a white truck and the driver died, and so on. So the reality is that the intelligent connected vehicle has the safety issues, safety challenges. We have to try to solve these safety issues and to achieve this expectation. So let's look into what are the safety challenges for the intelligent connected vehicle. So there are three main aspects of the safety challenges. The first one is functional safety. We call it FUSA. The second one is SOTIF. It is safety of the intelligent functionality. And the third one, or the third aspect, is cybersecurity. As we know that FUSA, the problem caused by the failure of electronic and electrical plugins in the vehicle, there are almost a clear standard ISO 26262 and more standard specifications. So it is mature at this time, at least in academic research area. And the cybersecurity, we think cybersecurity is finally solved or controlled by the government's legal constraints. So SOTIF. So the SOTIF problem is mainly caused by the performance limitation of artificial intelligent algorithms, insufficient system functions, and misuse by personal humans. So which is the main or the biggest problems in research and commercialization. So what is SOTIF? The SOTIF, the safety of the intended functionality, in ISO 21448, it gives this clearly definition of the SOTIF. So in this standard, we try to make some method to reduce the SOTIF challenges through the three aspects of effort. The first one is functional improvement. Second one is operational design domain limitation. And the third one is a test results assessment. So we defined the 4 area of traffic scenarios into these parts. The first one is safe, non-safe area. So this is the first area. It is called non-safe area. The second one is non-unsafe area. And the third one is unknown unsafety. The fourth one is unknown safe area. So we think that the first one and the fourth one is safe, so we don't care about it. But we try to reduce or limit the unsafe known area and unsafe unknown area 3 into the first one. So this is the main goal for the finished or the development of the ICD. We tried to minimize the area of second and the third one to enlarge the first one, the safe, non-safe area. So this is the general idea of what is the SOTIF and what is the main goal and what is the main approach to reduce the SOTIF challenge. So we summarize that SOTIF focus on functional insufficiency, performance limitation, and the reasonable foreseeable misuse. And the third part scenario is unknown and safe is the hardest or the main challenges part for the SOTIF issue. So this is the definition of SOTIF. Let's move on. So what is the typical cases of SOTIF? Why we think SOTIF is both engineering and academic problem? So let's see some typical cases of SOTIF. The first one is one automatic vehicle hit a roll-over white truck. We can see that this white truck lied down on the road and the automatic vehicle crashed it without any deceleration. So the cause of this accident is because of unidentified white truck compartment. So this is because of the perception limitation. The second one, we can see that this automatic vehicle hit one pedestrian crossing the road. It's just because a pedestrian violates traffic regulations. So the decision making or the path planning of automatic vehicle ignored or neglect the pedestrian violates the traffic regulations. So this is because of the decision making of the path planning algorithms in automatic vehicle. So the third one is a manned delivery vehicle crashed with one passenger car. So the reason of the accident is because private car suddenly accelerate. So the unmanned delivery vehicle can't respond to this suddenly accelerate. So we can see that insufficient algorithm performance, personal or human misoperation, unexpected traffic participant behavior are the inducement or the reason of SOTIF. So SOTIF of ICV, like the battery life of new energy electric vehicles, is very important to the safety of the people's life and property. So let's sum up. That's the long tail effect of ICV safety. So in the research and the development of ICV production, nearly 80% of safety problems has been issued or has been solved, but 20% of the SOTIF issues need 80% energy to be resolved. So let's see these typical SOTIF challenges. There are some unknown perceived target completely different from the conventional situation leads to an accident. The second one is unknown external environmental factors lead to system failure. And the third one is about the test. It's 1 billion highway test mileage still can't exhaust the unknown factors leading to accident. So 20% of the safety problems in the process of ICV development can't be solved, which belongs to the problem of SOTIF, which result in the long tail effect of the ICV safety. So there are many countries, many enterprises and universities started or they initially to work on this SOTIF issue, like in USA, Carnegie Mellon University, Stanford University, or MIT. In Canada, University of Waterloo, or Montreal, and the UK, and all of Germany. So Singapore too. So there are many countries is still working on or carried out the research in SOTIF area, but there is still lack of systematic research. If we look back into the international standard or some research reports they have published, and also some academic research from the universities, we can see that there is still lack of systematic research to occur or to conquer the SOTIF problem. So in China, SOTIF research is still at the early stage. It confronts many challenges, especially in the challenge scenario in China. So this is the first part. What is SOTIF for intelligent connected vehicles? So the second part is to how to solve it and what is the general roadmap to solve this SOTIF. So let me introduce with you one technical alliance to generate it, just to oriented to solve this SOTIF issue. It is CARCV, SOTIF Technical Alliance. So Professor Zhu Li from Tsinghua University, who is Chinese Academy of Engineering and also the president of China SAE, organized this technical alliance. There are 44 enterprises who are definitely or dedicated in this area to try to find the roadmap or the technical route to solve the SOTIF issue. And the objectives of this technical alliance are 4 aspects. The first goal is to promote the construction of test and evaluation system for SOTIF. Second one, promote technical research and innovation of SOTIF. The third one is about verification. So it is organized and promotes China's test and verification system and the capability building. The fourth one is to, through the research in this aspect, which can form large databases, scenario libraries, and standards related to SOTIF. So the general objective of this technical alliance is to promote the standardization process of SOTIF in China, to build a certification center and test laboratories, and to form large database, SIN database, and standards related to SOTIF. So guys, if you have any questions, please leave it in the QA area, okay? And I will answer you in the last part of this course. And the 5-year plan of this SOTIF technical alliance is we can divide it into 8 WP work packages, which is SOTIF scenario database construction, which from 2020 to 2024. And the second one is SOTIF frontier technical report and white paper on ICV safety. The fourth one is about test and certification system. And the fifth one is SOTIF optimization scheme design. And the sixth one is SOTIF safety analysis to train. And then research on SOTIF typical driving assistance system. And the 8th one is the OEM. We want OEM to report or publish the SOTIF research reports. So this is the whole 5-year plan of the SOTIF Technical Alliance. So based on this technical alliance, we summarize or propose the theoretical basis of sortive research, which is called safety entropy. So we see this ICD system as an entropy system. So the unknown scenarios. So this is the based entropy increasing principle in sortive scenarios, sortive systems, like the random and unknown scenario, AI algorithm uncertainty, and random or foreseeable human misuse, which will increase the entropy of the system. So how to realize the reduction of the system entropy? So we tried to use this approaches like 5G V2X enabled technology, improve artificial intelligence algorithms, and improve HMI, human machine interface design. So this is the theoretical base of sortive research. We call it safety entropy. And how to measure a quantification of a sortive? We call it safety entropy. Yeah, so this is the theoretical basis proposed by the technical alliance, and use this technical alliance proposed safety entropy. We designed some Chinese solutions for the sortive. So the first one is advanced sensor development, such as overcome the limitation of sensing functions, such as thin film image sensors and 40 millimeter wave radars. So this is about the advanced sensor development to improve the perception accuracy, like in ICD system. So this is the first solution is advanced sensors development. And the second one is improve AI algorithm. So this is the technology to improve the AI algorithm for the ICD system. Like we use the technologies such as data collection, continuous learning. VQ gain the ability to continuously learn and upgrade in real scenarios and establish an upgrade platform for ICD. So which is like our human being, we learned from the real traffic scenario and learned how to react with the edge cases or very challenging traffic scenarios. So after we try to learn from it and we upgrade ourselves ability to improve our driving ability. So this is second one is to improve AI algorithm. So the third one is digital infrastructure, standards, and equipment to support autonomous driving. So we call it CRSAD. So this solution is like the entropy system. We tried to use 5G V2X technology to improve our like perception improvement or use the infrastructure's information to improve our accuracy of perception, decision making, or other system or algorithms in ICD. So this is the third scenario, a sortive solution for the sortive CISAD. So research on the ICD lighthouse system established digital road infrastructure and provide consistent electronic and visual signals for vehicles. And then, which can support the realization of road set out vehicle is enabling technology services for vehicles, including high presence, coordinated vehicle road location, over the horizon recognition, and so on. So this is the effect or the importance of the CRSAD to solve the sortive issue. So there's one very simple application of the ISAD, like we can use the information from the instructor in the crossroads, and then we can tell the autonomous vehicle there are some unknown or unseen objectives in other directions. And this way we can improve the perception algorithms to our autonomous vehicle. So this is a very simple or very general application of the CSAD to improve or solve the SOTIF issue. And there are some other applications and other efforts which can be made from the CSAD. So the first one is the CSAD, which is called China Cloud Control Facility Standard and Automatic Driving Support Equipment. So this system is the basis of intelligent traffic and is responsible for processing traffic data. So CSAD system supports the self-driving vehicle group to realize the integration of the state data, intention data, and intelligent collaboration and integration, which is called negotiation. So this is called the CSAD. This is also one of the solutions to overcome the SOTIF issue. So we use the in and out vehicle enablers and fuse it together to reduce the fuse the redundant scenario sensing to reduce the area. The third one is unknown and safe area. So to enlarge the first one. So this is what is the general Chinese solution to overcome the SOTIF issue. And the main goal is to reduce the third area and to enlarge the first area of the traffic scenario. And by this way, we can reduce or eliminate the SOTIF problem. So based on the general technical routes, we can get the roadmap for SOTIF solution in China. So we sum it as three aspects or the three steps to solve the SOTIF issue in China. The first one is offline safety development for the ICD production. So which way we can combine the SOTIF concept with functional safety management in the VV strategy. It is from development and also the test, validation, and verification strategy. So this is called offline safety strategy. So the second one is online safety control. So which means we can get the online monitoring and online control for safety of the autonomous vehicle. So which can monitor the SOTIF issue or the SOTIF risk and then make the active control for this vehicle. So which we can call the online safety control. The third step is active ongoing learning. So which like what we have introduced, like improving or gradually improving AI algorithms improvement. And this is like a human being learning from the real traffic data. We collect the real traffic data and to use it to learn from the active learning platform to improve our ability of this automotive vehicle. So this is the three steps on the roadmap for SOTIF solutions here. The first one is offline safety development, and the second one is online safety control, and the third one is active ongoing learning. So in the previous slides, we learned that the general technical routes or the roadmap for solving the SOTIF issue, and then how we can solve it or how we can reduce the SOTIF issue in academic research area. So the third part, I will introduce what we are doing to reduce the SOTIF issue for ICV, especially for the autonomous platooning. So the third part is I will introduce from academic aspect what we can do to reduce or eliminate the SOTIF challenges for autonomous platooning. So first, let's review what is the typical SOTIF challenges for autonomous platooning. So there are several slides which can be shown that the SOTIF challenges for this platooning issue. So the first one is the performance limitation of perception system, insufficient perception and cognition in complex environment. So this is a very clear problem. Like if we drive the vehicle or drive the platooning in a severe or very crowded traffic scenario, it might be caused some perception errors. And the second one is performance limitation of decision-making system. There are some errors in prediction and decision-making in complex traffic scenarios. Yeah, and the third one is the performance limitation of execution system, such as the accuracy and the time delay of the execution system. So this is the performance limitation of the execution system. And of course, there is one human misuse aspect. So this is caused by the drivers or the passengers. So there are four aspects, main aspects, which tell us what kind of sortive issues for autonomous platooning. And for detail, so this part may be, we can see that it is a general sortive issues for all the SCVs. So what is typical of the specific sortive challenges for autonomous platooning? So let's review it. So the first one is infrastructure and external factors. Like the platooning running on the road, if there is GPS signal losing approaching construction area, so this is the sortive issue from the infrastructure and the external factors. So from this aspect. And the second one is the emergency brake. Emergency brake would cause the instability of the platooning itself. So this is vehicle within platoon emergency brake, so which can cause the sortive issue too. The third one is cut in or cut out of the autonomous platooning. So this is external vehicle cut in or the vehicle in platoon, they drive away from the platooning. So this is the cut in or cut out of the sortive challenges for autonomous platooning. And there are some communication issues like the time delay, package dropout, or receiving problem, uploading problem. So this is from the communication issue of the platooning. And there are also some other sortive challenges like specialized function, increasing the spacing policy, increasing the cruising speed, platooning reformation, and accidents within the platoon. So there are also some errors or some causes from sortive challenges from human being. So such as operator misuse, the operator take over driving authority, leading vehicle unexpected lane change, and also following vehicle unexpected lane change. So these are all the sortive challenges for autonomous platooning especially. So there are great challenges for autonomous platooning, which includes infrastructure and external factors, emergency brake, cut in or cut out, communication problems, specialized function, and operator misuse. So these are the main or typical sortive challenges for autonomous platooning. So how to solve it? And we summarize the sortive challenges into three aspects. The first one is the operational design domain variable, and it will bring the challenges. Random risk identification is hard on real time. And this is because of the operational design domain, like the rainy day, foggy day, slippery road. This is kind of operational design domain. The identification of this kind of random risk would cause sortive challenge. So it is hard to quantification or identification in real time. So the second challenge is because of the artificial intelligence algorithm. So which is the main aspect of the sortive issue, because the artificial intelligence equipped on the car is black box. It has uncertainty and black box characteristic. So its uncertainty risk quantification is hard. We don't know what it is known and what is unknown. So the artificial intelligence algorithm is the main challenge or the main sorting issues. We tried or we have to quantification of the artificial intelligence, its health state or its uncertainty state. We have to quantification the algorithms equipped in the autonomous vehicle. So like what we have learned from the very beginning that Tesla or Uber, they have different kind of accident because of perception algorithm or decision-making algorithm. So the algorithm, AI algorithm equipped in the ICV is the main challenge or the main problems or the sortive challenge. So the third one is a safety deficiency. We have to try to protect the safety, the driving safety in real time. So this is the three aspects of challenges for autonomous platooning: the ODD variable and the AI algorithm uncertainty and the safety deficiency. So the driving protection. These are what kind of sortive challenges for autonomous platooning we submit. But how to protect it and how to solve it? We established one self-surveillance and self-adaptation system. So let's see what is this system. So in the car, in automotive vehicle, we can see that there are some sensors like LiDAR, radar, camera, or RCU, internet. And we have the master control in vehicle, so like localization, perception, prediction, and also decision making and motion control. So this is what is the original system in the autonomous vehicle or in the ICV. So we propose one special or independent unit to monitor the state of the system and ODD, and then try to protect or try to guarantee the safety of the system. So the first unit of this system is called AI, Artificial Intelligent Real-Time Self-Surveillance and Self-Adaptive System. So this part can monitor the health state of the perception, prediction, localization, this kind of artificial intelligent algorithms health state, and trying to make the safe decision. So this is the first part. For the monitor the artificial intelligence, which is the most important. I think this is most important in this system. The second one is ODD, real-time surveillance system and self-adaptation. So ODD means operational design domain. We can monitor the weather condition, road condition, and V2X communication, the situation. So based on the monitor results, we can make the safe decision. So this is the second part for the ODD variable challenge. The third one is a traffic law digitalization. So this part, we tried to, based on the assumption that if all the autonomous vehicle or the ICV running on the road obey the traffic law, there should be less traffic accident. So we add this unit into the system to promise our vehicle is obeying the traffic law when it is driving on the road. So we try to use a traffic law to monitor whether this system is obeying the traffic law or not. If not, we try to give the suggestion to promise the safety of the decision making. So this is a 3 units of the self-surveillance and self-adaptation safety system. So I will introduce some part of this system due to the time limitation. And the first one I will introduce is the perception real-time self-monitor or self-surveillance and self-adaptation system. So perception challenge are emerging endlessly, like the Tesla accident, and there is one accident happened in 2016 in China. So this is all because of the perception system is misjudged from the objectives. So handling the perception uncertainty of the semantic results from perception algorithms is one of the biggest challenge in SOTIF. So how to solve it and how to solve this problem is based on how to quantification of the risk of the perception issue, right? So based on this question, we summarized or established one perception SOTIF scenario database or dataset. We collected the perception failure scenario, like it is a rainy day, like rain stains, rain streaks, haze, and such as the light, headlight full beam, reflection, glare, and so on. And the snow day, like snow stains, snowflakes, haze, and snow covers. So like foggy day is scattering, haze, and candle effect, and so on. And also some unusual morphology, like design, posture, appearance. Yeah, like this. It is hard to recognize whether it is a person or the big beam, right? So especially it is difficult for the autonomous perception system. The same way, like a rainy day, foggy day, snowy day, and some light, which can cause the perception algorithm's failure. So considering the multiple perception failure problem, more than 300 SOTIF-related scenarios have been collected in this dataset. So next, we tried to quantification of the SOTIF issue for the perception algorithms, which is called onboard artificial intelligent health monitoring. So we use the deep ensemble approach to abstract the uncertainty information for this perception algorithm. Like after the perception algorithms, we can get the spatial information, semantic information, and also the uncertainty information. So like the red one, so which we can call it is uncertainty. So the uncertainty, we divide it into low uncertainty, high uncertainty, and medium. So based on this technique, we are not only to get the object classification, but also we can get the uncertainty of the artificial intelligence algorithm, which means how we can believe the algorithm's output. So it is deep into the artificial intelligence algorithm itself. It is different from what we can see from the literatures, what they can do, the classification. But use this quantification results of the SOTIF issue can be realized in real-time alerting that if we can detect some objectives, it is the uncertainty is high, which might utilized in real-time alert and can transmit it and model into the decision-making module. It is called systematically to consider the SOTIF risk for perception system. So there is one case we tried to recover one accident happened in 2016 in China. This is the first accident caused by the automatic technology in vehicle. So there's one vehicle. It is maybe a vehicle working on the road, construction vehicle, and the vehicle equipped on the autopilot autopilot. It is an ADAS system. It can't detect this construction vehicle and crashed. Unfortunately, the driver has died. So let's see the accuracy of the safety alert. So we can see that before the vehicle crash with the construction or the big truck, it can show the uncertainty is high. Just imagine if we implement this technique into our ADAS system or ICV, which can make the alert in advance and try to prevent this accident, right? So this is the accuracy rate of the safety alert reaches 97.71% and utilized on the onboard AR health monitoring algorithm. So once we got the perception uncertainty, we can discover or propose the perception uncertainty aware decision making, safe decision making. So we extract the uncertainty of the perception algorithm and try to inhibiting factor of algorithm risk. And we use the artificial potential field-based inhibiting factor just to combine the driving risk and also the risk from the perception uncertainty. Yeah. And then we can make the minimal risk decision-making strategy. So this is a perception, self-surveillance and self-adaptation system. So in the AI real-time self-surveillance, I will introduce another one. It is for perception real-time monitoring or self-surveillance system. So in the real time, there are some challenges caused by the prediction algorithm, like some unpredictable behaviors in the surrounding vehicles, especially when we don't know when will it cut in or cut out. So this is called unpredictable behavior of the surrounding objectives. So it is hard to believe just on the prediction algorithm, like long short-term memory algorithms. So it is a very common used prediction algorithm, but sometimes the algorithms has uncertainty too. And then we try to discover or abstract the uncertainty of the prediction algorithm. We also use the deep ensemble as approach to abstract the real-time uncertainty estimation. So this is the overview or the structure of surrounding vehicles motion prediction and uncertainty estimation. So based on this technique, the prediction uncertainty is acquired by the calculating the aleatoric uncertainty from the scenario and combined with the epistemic uncertainty of the prediction model. So from this, based on this technique, we are not only got the predicted result, like what's the position and what's the velocity of the surrounding vehicle. At the meantime, we can get the prediction uncertainty from the algorithms. So based on this kind of information, we can definitely make safer decision making, which combined or consider motion prediction uncertainty estimation. So how to include motion prediction uncertainty in this decision making system? So this is the framework of the uncertainty aware decision making with prediction uncertainty estimation. So this part is how to get or how to abstract the uncertainty estimation, and then we try to implement into the model predictive controller through the uncertainty aware potential field. Of course, it combined the prediction model and multi-constraints of the dynamics. And then we can design the decision making with motion prediction uncertainty estimation. So through the results, we can get that the uncertainty aware decision making is developed to lower driving risk. So this is the AI real-time surveillance and self-adaptation system. And the second one I want to introduce is the ODD real-time surveillance system. So how about the weather condition, road condition, self-surveillance, and communication, V2X communication, real-time self-surveillance, and the self-adaptation. And due to time limitation, I will introduce weather condition and communication self-surveillance system. So for the weather condition, as we know, the water drop and the fog will block out the object, affect the image, and reduce the visible distance and the performance of the perception system. And also, the weather condition can affect the lower friction and affect the safety of the vehicle when driving. So considering the influence of weather condition, like rainy days, snowy, foggy, on autonomous vehicles, safety driving constraints are provided for autonomous vehicle to reduce the safety risks based on the surveillance of weather condition. So taking a rainy day as an example, the image recognition network is used to estimate the amount of rainfall based on the residue, and the rainfall is taken as a system input to make the corresponding safety decisions. And also based on the influence of the rainfall on the visible distance and the thickness of the water fill, the reasonable speed under the constraints of braking distance and the sleeping distance was calculated to reduce the risk of driving. So this is the weather condition. It is such as mainly based on the engineering work. So it is not hard to detect the weather condition. We can use different kind of technologies like the perception algorithms, and even we can use camera or lidar to detect the foggy and visible distance. And also we can use some techniques to alert or to reduce the speed limitation. So this is a kind of, I think it is most engineering problem. So the second part in ODD real-time surveillance system is V2X communication. So which is typical challenge for the autonomous platooning. So as we know that for the platooning, the time-varying communication delay and the packet dropout in V2V communication will affect the longitudinal stability of the platoon and may trigger the safety risk of the platooning. So, especially for the platooning of the vehicles is a multi-objective problem, which needs more than just a longitudinal control. So based on the literatures we can found all the systems has been implemented in the enterprises, which almost consider just the longitudinal control. But we think it is not enough for the safety of the platooning. So we try to propose or establish one distributed robust controller framework, which can solve the problem of the like V2V communication time delay or packet dropout, and also we can combine it with the lateral control with the longitudinal control. So there is one novel distributed robust controller framework with crash mitigation is designed for platooning to deal with the complex traffic scenario under V2V communication delay. So considering the influence of V2V communication packet dropout and the time delay on longitudinal platooning stability, the H-infinity control or state feedback controller is designed to reduce the safety risk in the platooning. So the H-infinity controller or the H-infinity state feedback controller is designed to reduce the safety risk caused by the packet dropout or the time limitation or time delay of the communication. And there is also, considering the influence of time-varying delay, a proposed distributed robust controller which combine the longitudinal and the lateral control together, successfully solved the crash mitigation scenario in which the target line is blocked by the obstacle vehicle. So this is one of the application of this distributed robust controller framework for plantooning. So this is the movement of the plantoon, position errors, and also the velocity of the plantoon. So through this research, we developed the whole system of the self-surveillance and self-adaptation system. There's one more, is traffic law digitalization. So based from the beginning to introduce this system, I put the assumption that we assume if each vehicle running on the road obeys the traffic law, there should be less traffic accident. So this is the assumption. So based on this assumption, we tried to implement the traffic law into the decision making. The one reason is to monitor whether the vehicle is obey the traffic law on real time, and the second reason is we can implement the traffic law into the decision making to make it safer. So based on the regulation on the implementation, traffic law is classified into speed, distance, line, right of way, and others. Different decision making implementation methods are given based on this classification. And according to our decision-making system, it is MPC, Model Predictive Control. Based on this framework, all kinds of regulations on the implementation are classified into different implementation ways, like the speed, which can be transferred into constraints and the references, and distance can be transferred into constraints and cost, such as, and so on. The lines like reference and weight, we can implement. So implementation are classified into different implementation ways, and the implementation of each regulation may correspond to the modification of multiple contents of the decision-making system. So this is one typical traffic law digitalization. So this is one example. So this is the traffic law. On the road without central segregation facilities on midline, when any motor vehicle faces motor vehicle approaching from the opposite direction, so each shall slow down its speed and keep a necessary safe distance from other vehicles and pedestrians. So we try to digitalization of the traffic law and implement into our decision-making system. So this is what we realized. One example, this is the example. So the implementation of this regulation corresponds to the modification, potential field, and the cost function. So this is how we can digitalization of the traffic laws. And this is, by now we have introduced the whole system for self-surveillance and self-adaptation safety system, which can be divided into 3 units. The first one is artificial intelligent surveillance. Second one, operational design domain, self-monitoring and self-adaptation. And the third one is traffic law digitalization. Based on the monitoring of self-surveillance system, we can make the self-adaptation system decision-making and the planning. So based on this system, how we can test this system, we built or established one sorted scenario library. So we proposed one sorted system architecture for the scenario. So we collect the data from academic knowledge analysis, OEM Tier 1, Tier 2 development experience, and government accident database. We collect the data and tried to analyze the sortive limitation of the sortive element from the perception, decision-making, HMI, location, or actuation. So we use the data to analyze which are the elements of the sortive issue. And based on these factors, we establish the sortive scenarios architecture. There are 7 layers. So the first layer is the road structure. Second layer is infrastructure. The third one is temporary manipulation. The fourth one is traffic participants. The fifth one is natural environment. The sixth one is intelligent connection or the communication. The seventh layer is a vehicle inside information. Yeah, so this is the sortive scenario architecture based on the analyzation of the data source and the sortive limitation. So this is the library. We collected millions of data provided by participant group, which I have explained, which is the sortive technical alliance. So there are 18 members from the technical alliance. They uploaded, analyzed, processed, and studied according to the proposed scenario architecture through this. It is called shared scenario library, and we can generate the test cases for the subsequent research. So this is the structure inside of the shared scenario library, like a statistic part, dynamic part. So all the information of the scenario can be uploaded in this website platform. So this is how we test the system, how we can generate the test cases. So we use the sortive scenario libraries and how to implement. If we want to implement this self-surveillance and self-adaptation system, we have to modify the autonomous driving function framework. So this is the modified autonomous driving function we combined with one project with Jiefang FAW. So we implement or insert the system self-sensing and monitoring and emergency function in this autonomous driving functional framework. So at this moment, we are trying to implement the sensors and also the computation unit into this vehicle. So this is the test vehicle from FAW. We tried to implement our self-surveillance and self-adaptive system. So due to the copyright of Jiefang FAW, so I didn't put the sensor information here, but we can see that the right part is a regional autonomous system, and the green sensors computation system. This should be the green one, is the self-surveillance and self-system. So we are going to test it by the end of this year or in the early stage of next year. So this is how we develop the self-surveillance and self-adaptation system to protect the safety of the autonomous platooning, especially for the sortive issue. Okay, thank you very much. This is what I present today. And if you have any question, please leave it in the QA section and we can discuss it later. Thank you. So do you have any questions? If you have any questions, please leave it now. And I see there is one, it's not like a question. It is called, he's listening.